I'm Timothy Prickett-Morgan, co-editor of the Next platform. Today we're going to be talking about how silicon photonics is going to enable disaggregated architectures for HPC and AI systems at scale. Just to let you know, we're going to be monitoring the chat sessions throughout the webcast, and for the Q&A we'll assemble those and answer as many of those as we can in the last 15 minutes of the broadcast. We have a lot of ground to cover, and we're going to just start by introducing our panelists. I'm going to do it in alphabetical order by organization. So we're going to start with Mike. Tell us a little bit about yourself.
Hi, so this is Mike Ignatowski. I'm a senior fellow at AMD Research, specializing in advanced memory architectures and photonic interconnect.
Hugo, that makes you next.
Hey, Tim. Good morning. Hugo Soleil. I'm the Vice President of Marketing and Business Development at IR Labs out here in California.
Ian?
Ian Carlin, Principal HPC Strategist at Lawrence Livermore National Lab in our Advanced Technology Office, looking at future technologies for systems and our application performance.
Craig?
I'm Craig Prunty. I'm VP of Marketing and Business Development for Cyprel in Europe, in France.
And Mark, you're last.
Hi, I'm Mark Parsons. I'm the Director of EPCC, which is the Supercomputing Centre at the University of Edinburgh, and I'm leading the UK's Exascale programme.
Welcome to you all. We've been talking about silicon photonics for a very long time. There's been a lot of advanced research. We see some development and some productization of this. Why is silicon photonics actually happening now, and why is it important that it's happening now? Ian, we'll start with you.
Yeah, so I think part of what's happening is we're hitting the end of the tricks electrical people are able to play, right? They're running out of steam. They've pulled more rabbits out of their hat than we expected, and now you're hitting that end, as well as there's just the slowing down of compute and other things that are driving the need for more bandwidth a lot quicker than people have expected.
Hugo, I mean, you work at a company that's advancing this technology, so why do you think it's happening now?
Well, I think it's like what Ian said. It's, to some part, it's, the electrical tricks are running out of steam, but there's just no end in sight in the amount of data that's being moved around, whether it's within a supercomputer, on your laptop, in the internet. The amount of data is growing at such a fast pace that there's always a need to improve your I/O network, right? So from a demand perspective, I think there's plenty of it out there to keep improving the technology. From a supply perspective, it's really the right time. It's the point in time where things are maturing. At IR Labs, we've been developing this technology for over a decade now. And it's a combination of getting the right suppliers in place, the contracts in place with high volume manufacturers on the laser side and on the silicon side, and it's really all coming together at the right time right now.
Craig, you think that's true? I mean,
I think
systems. I mean,
so the thing I think we see with systems and chips both is we're seeing more and more disaggregation. We're seeing on the system level, people are looking at composing elements, whether it's in the server, whether it's in the rack, whether it's beyond the rack scale, and even in the chip, you're seeing the same trends. So looking at ways to get more data bandwidth and lower latency are high on the list of goals. And if you can do that and also make, let's say, distance less of a factor, it's all the better.
Mark, what do you think?
Yeah, I think, well, at some level, this is something of a holy grail, isn't it? I think we've all sat in many presentations over the last decade where people have talked about this. I think there are a number of things happening at the moment that are causing people to think much more clearly about how they bring systems together. And I think part of what's driving this actually is this convergence of the high performance computing world with the sort of AI data science world and how we connect those two worlds together. I think that's a key driver in all of this.
Mike, that leaves you as my last one to open it up.
Sure. The way we tend to look at it is that the cost of optics has been coming down for quite a while. And with the next generation of silicon photonics, it looks like the cost could take a step function down in terms of cost per bandwidth. So that suddenly makes it very interesting for co-packaging optics on our components. That plus the area of the photonics picks and the power per bit transmitted, quite frankly, are looking really good in the next generation of photonic components. Plus the number of electrical pins that you can get out of a socket has pretty much reached its limit, and we still want to keep pushing up the bandwidth. So we're looking at ways to do that other than just more and more electrical pins coming out of the bottom. So this is why a lot of people, including AMD, are seriously looking at co-package optics in future generations coming up.
If the optics is coming down in cost, and is the electrical also going up and the complexity is going up? Is that happening as well, or is that still very inexpensive and expected to stay very inexpensive in the long run?
One of the problems is that the CMOS support for high-speed I/O is not really improving much. It's stopped improving a generation or two ago. You're just not getting the benefits of high-speed analog I/O that you can get for digital. So it's becoming more and more of a challenge. It's not dropping in power. It may actually be going up a little bit, and it's certainly not dropping that much in chip area anymore. So it's getting to be more and more of a challenge.
Gotcha. So disaggregation and composability are the key drivers, or two of the key drivers for silicon photonics. I think those are drivers in the data center separate from photonics, but photonics can kind of help the situation along, I think. Obviously, when you architect systems, if this stuff becomes commercial, you're going to have a much broader palette with which to kind of create systems. I find that very interesting. But I'm also a little disturbed that I won't quite know what the unit of compute is anymore. I'm used to thinking of a chassis and then a cluster of chassis to make a distributed system, and I can sort of get my brain wrapped around that. But when everything is sort of composable in racks and what's really part of the system, what is the system? It's almost the system will be composed on the fly at that second, and that's what it's going to look like. So what are your thoughts about how the architectures are going to change and how people will have to think about systems when this disaggregation and the photonics come together? Craig, I'm going to start with you.
Well, so what you're talking about sounds a lot like cloud right now, in terms of you can select what kind of compute you want, what kind of storage you want, what kind of programs what kind of composability you want on top of that. I think HPC systems in general, you're looking for as much compute as you can get, but you're scheduling what compute is allotted to you in your time frame. So I don't think that putting optical interconnect is going to change that in either case, right? You have the compute you get the time you get, and you pay for the service you take. I think what it does is it actually allows you a better selection of the elements you want, as opposed to taking the composable units that are provided based on the silicon that exists today or the server that exists today. So I'm going to turn this light off. I'm getting a strobe light effect. Sorry about that.
And you have to be involved in the acquisition of some of these large exascale systems now and figure out how the applications are going to work. What happens when we're not sure what the unit of compute is? Is that a good thing? I assume it is.
It's a good thing for a lot of these emerging work flows where people, don't always want to mix and match the ratio we're currently putting in the server for them. Either they want more bandwidth than they can get into a GPU, or they want fewer CPU cores than they're getting, or they want more CPU cores and less GPU than in your Sierra or eventually El Cap. So they're not stuck with kind of that. They can mix and match and get the right amount of CPU, the right amount of GPU, the right amount of a new accelerator to improve the efficiency of their job. They're still going to be limited by what's on that high-speed interconnect. I mean, that's going to be the edge of the system. There's going to be some fall off because at some point it either becomes too expensive or impractical to wire together a machine that's, spanning multiple buildings or even maybe filling up a full building at that connectivity. So that gives you kind of that limit of your machine, but it allows people who aren't running on the full system which is, most of the jobs. There's a lot of jobs at that quarter, third system level to get the ratio they want. The scheduling software people have a massive headache of how to deal with users at that point. But for a user, and especially a lot of these new workflows that are combining multiple physics codes back to back or AI, this becomes, game changing in what they can do.
Mike, what would happen if this was available today? I'm sure you at AMD were wishing that this was fully commercial and ready to be part of the first exascale machines that you're building at Oak Ridge and Livermore. What do you think about, how this could be used in future systems that follow this?
Yeah, unfortunately, it did not come in place in time to have a big impact on the exascale systems, at least the first generation of them. Second and third generation, now we keep wanting to double the performance of exascale systems based on historical trends, so they can have a big impact. The way I look at it is, historically, there's a big discontinuity in bandwidth once you cross the package boundary, drops significantly. And then once you leave the motherboard, there's another discontinuity in bandwidth. And this impacted the way you build systems and think about systems and the way you program systems. And what optics does is allows you to smooth over those big drops in bandwidth.
And can't you just put in like 8 200 gig InfiniBand cards and that solves everything? I mean, that seems to be some attitudes. I'm being extremely facetious.
Yeah. There's even trying to get to those InfiniBand cards is going to be problematic. I think it changes the notion of what a server could be. And I sometimes joke that we talk about disaggregation. We might have the terminology completely backward, because what you're trying to do logically is aggregate components together into a server that you couldn't really do before because of the big discontinuity in bandwidths and latency. But now optics makes that aggregation of components together possible for the first time.
So we should be calling it decomposing and aggregation, not disaggregation and composing. As the English major in the room, I can tell you, I think you're right. Mark, what do you think? If you could have had this stuff already, would you have been excited about building systems with it?
Yeah, I think so. I think it is a little bit like the discussion about cloud, in as much as you end up in my job with people trying to sell you things, solutions in the cloud where everything's infinitely scalable and nothing will ever break. Now, in truth, we all know that at the end of the day, there's a computer at the end of that wire. I think one of the key challenges I have in running a big data center now is I'm spending more and more and more on transceivers. I said this when we were discussing this the other day, and I think just last month I spent $130,000 on transceivers, and I can't just continue to do that. And the idea as well that I'm taking an electrical signal off a pin, I'm moving it across a trace on a motherboard to another bit of silicon that then converts it through a connector into an optical signal is just silly at the end of the day, right? It's really power hungry and it's really inefficient. And we just have to move to this world where we've got optical signals coming off processors and off memory. And I think what surprises me is that it's taken so long for people to get to this point of actually seriously talking about it.
Well, I know that you're not the only one who feels that pain. Facebook, for instance, skipped the 200 gig Ethernet generation entirely, to the great chagrin of Arista Networks and their financials, because they said, no, that cost per bit's too high. See you in 2 years. So yeah, the pain it's uniform out there wherever there's lots of scale. It's absolutely painful to pay for the cabling and the transceivers. It's crazy. All right, so we talked a little bit about the hardware. Let's talk about the software. For any good technology to be absorbed, it has to be painless or seamless or transparent or invisible, even better still. What kind of pain are we looking at when we change the I/O in these systems, and we change the way memory is scattered around, and we change the way that I/O is done when it's disaggregated? I want to say decomposed, I guess. Ian, what is the pain going to be involved here in the software? Because man, I've heard the hardware promises so many times, and then the software doesn't come through. How's it going to work?
It'll be baby steps, right? If we keep it baby steps, you're gonna, have the software people not scream. You're not gonna, if you break people's MPI, if you break how they think about memory at the beginning, it's never going to get adopted. But if you allow it to be so that what people are doing today works, or works maybe a little bit better just by switching this technology, and then you allow them an entry point to move to something where there's a carrot, that's how you kind of get users to move on to new technology. As I said, the schedulers and the other system software are going to be what's going to be the challenge first. Just how do you start to manage a system where instead of having 10,000 exactly the same nodes, to now I have 500 of this and 10,000 of this, and you have to ask for how many gigabytes of memory you want, and making sure the machine stays busy is going to be a challenge. That's going to be an optimization, which will be great. But I think the system software is going to be the challenge first, as long as people accept the fact that you're not going to get the full benefit from this out of the gate. You're going to get incremental improvements over time.
Are the degrees of freedom so complex, and the number of things that could be interconnected so complex that it'll be, is this a natural thing for AI to actually do? Will we have, I'm going to call it a hardware compiler, that does this and figures out the optimal way to glue things together for the workload you've just submitted. Ideally, you don't want to set up the system first and guess, and then throw the applications at it. You want something that actually knows what's available and knows what's in the queue. This is going to get complicated. So how's that going to work? And who's going to write this software?
I think you're right. Maybe it'll be AI. I think the other thing that will happen is you'll start with, disaggregation at, a few server scale, and then move up to the rack scale, right? People are going to slowly make this more complicated. If you just can't dump, the data center scale disaggregated system with random components on people at the beginning, or you have to introduce just a couple pieces of disaggregation where you have 3 or 4 processor types instead of the 2 that we typically have in most advanced systems, right? So if you keep it simple and phase it out, people will grow into it, like we've grown into accelerated systems where they're having more and more GPUs per CPU. But you just keep, the hardware people will always be able to do more than the software people can absorb, and someone just has to put the leash on them and keep pulling them back, and letting them run, but not letting them run fully free.
Don't pull your arm socket out. Hugo, you had some experience with this in a past life, working on silicon photonics at Intel, and then now you're doing it at IR Labs. So, what do you think about the software stack? I know you're a hardware guy now, and that's not your problem, sort of. But how are we going to make this all work, and who's going to do it? That's what I want to know. Everybody can't home grow this.
Well, the hardware is not going to work without the software, right? So both have to come together to make good things happen. But one thing I want to inject here is disaggregation doesn't have to mean you're pulling everything apart. And if we go back to the idea of composability, maybe you want to compose a very large memory, shared memory machine where you're taking 8, 12, 16 servers and making it just look like one big scale-up machine. That and maybe that's back to Mike's point about we should be calling it composability and versus disaggregation, right? Sometimes maybe what you need is just a really large pool of memory, and that pool of memory is shared. So I think there's going to be a few different ways that disaggregation and composability is, going to make its way into data centers, and it's going to come down to the applications and of course the vendors pulling it all together. But I think there are baby steps. I think the idea of everything is completely disaggregated, just blowing up the entire data center and putting just big pools of processors and memory.
No, that's my dream. Don't destroy my dream. I want that.
I'm sure it's going to
I
come.
want infinite degrees of freedom.
and I'm sure the industry will give it to you, Tim.
I've
It's
been
just
waiting a long
I
time. I think I wrote Smashing the Server 10 years ago. Craig, what do you think? You're laughing. So,
well, just thinking of Gallagher smashing a server, but maybe that's dating me. So
I could
a
get
couple things. Yeah, exactly. A couple things come to mind. One is if you look at architectures today, whether it's system architectures or chip architectures, so you're seeing more and more coherency. And from a software perspective, at least at the chip level and the server level, the closer you can get two coherent elements together, the easier the software gets. So reducing that latency. So let's say at the workload level or at the server level, I think the software gets easier if you have coherent connections that are shorter latency over longer distances. That gets easy. The orchestration side, I agree, but you're already seeing modular architectures for HPC. I mean, people are putting in neuromorphic modules and obviously GPU modules or other accelerators, right? FPGA or other kind of acceleration elements for AI. So you're already seeing a variation in the type of processing in the entire system. You have to orchestrate that somehow. So whether that now becomes broken into smaller and smaller bits, I think, yeah, it's more challenging, but I think it's going to be an incremental upgrade over time. You're going to see some disaggregation at, let's say, the board level, and then at the server level. I think this is what Ian was saying earlier, right? And I don't think exploding all at once, that rarely happens in the industry, right? That takes that's a big step function. Something has to happen to drive that.
And some of the vendors who have tried to do that, and I have great respect for them, they did not do so well. So
don't be wrong about that kind of big change. It's really expensive. Yeah.
Absolutely. All right, Mike, you're a hardware guy, I suppose. So talk about software a little bit. I know it's probably not your problem.
Well, first, let me say that, Tim, you introduced the word decompose or decomposing. And I strongly suspect that every marketing group in every company is going to discourage.
My farmer's coming out. That's compost. It's all good.
Except cleaning companies, right? Yeah.
My money is that it will not catch on much in the industry.
Fair enough.
When you think of software, the collection of hardware resources that an operating system managed was usually what defined what a server was. And then that started breaking down when you get to hypervisors, and then breaking down further when you get to a hierarchy of cluster management software. So it is becoming very difficult and ill-defined about what a server is anymore.
Well, I don't want an operating system at all, but that's a totally separate conversation. I want runtimes and DPUs and get it all off of there and stop wasting that CPU. But that's just my opinion.
I suspect for a lot of applications, the big boundary is when you have to start thinking about going over Ethernet or InfiniBand as opposed to staying on a local network. That's where they have to start doing things differently. And the other boundary, as Craig mentioned, was that when you are on a coherent shared memory and then cross the boundary to no longer being on a coherent shared memory, that's the other thing that causes software to do things differently. Mm-hmm. So I suspect those are the main boundary conditions and walls that the software has to worry about right now.
Yeah, I like the idea of the network being the boundary of the system and the coherence having its own boundary within that. And then you can do different things inside of it. I personally would love the coherence to be as big as possible because you can do more interesting things with it. But anyway, Mark, what do you think about all this?
So I think you've got to think a bit in this context about when memory is memory and when memory becomes storage. And the really interesting thing that happened a few years ago was Intel kind of getting itself confused with what it ended up calling data center persistent memory, but which was its 3D crosspoint product. And that proved really confusing for people to use because you could either use it as memory, or you could put a file system on it and use it as storage, or you could do a bit of both. And I think that
it's difficult. It was hard to program.
Exactly. And I think that caused lots of confusion. But really, we work with that. I did one of these European research projects with it. And we added a whole lot of functionality to Slurm, so Slurm knew where data was between different jobs, and it could go off and find it and schedule the job on the resource where the data was. All worked really nicely. So if you start thinking about this from a software point of view, at the end of the day, what's an operating system? It's just a scheduler. It's just managing queues. So don't call it Slurm, call it the operating system, and think about how the operating system is handling that data. And then you've got to think about how that data is represented in the memory. And I don't think we've had many of those conversations yet, but it applies to this. I think it's really, really important here.
All right. So let's talk about how we might do this. There have been a lot of interconnect standards, and get your alphabet soup out, because here we go. CXL out of Intel, OpenCAPI and CAPI out of IBM, NVLink out of NVIDIA, C6 out of AMD, and Xilinx and a bunch of other people. There's PCI Express. So it looks like CXL is emerging as kind of the de facto standard for the way you want to connect accelerators, network devices, and CPUs together. Again, there's some coherence. It's not precisely the kind of coherence I'm dreaming about, but it's going to get us close enough that I think we can do something useful. So what's the question, two-parter here? So what's the prospect of CXL being the standard that we can all rally behind and we can finally get moving on how we glue this stuff together with that with that protocol? And then what are the odds that we can come together and get an optical transport to use? Because I don't care about PCIe 7. I don't believe in PCIe 7 at the time when it's there. That's the equivalent of caring about a PCI or PCIe card today. I'm ready to move on to optics, and I assume a lot of people are too. So, Ian, I'm going to pick on you first again, because you think about applications first always.
I mean, the application people don't really care what the transport layer is. We just care that you can actually connect, the devices we want to connect together in a way that's programmable and easy. So, I mean, to some extent, we care about the end result, not what the standard is. The standard enables, treating an accelerator in a better way than we currently have, where there's multiple options, and that causes problems because our people have to write code sometimes to the lowest common denominator, which for GPUs today is PCIe Express attached GPUs. And so anything that raises the lowest common denominator in particular is almost more valuable than where the top end is.
Understood. Hugo, what do you think? I mean, can you take the technology that you've developed and can it support CXL?
Oh yeah, I mean, absolutely. And I think, the ultimately the market's going to dictate which protocol wins, right? And CXL certainly does seem to be winning. It seems to be a standard that's being adopted by every major chip vendor out there. It may not be the solution for every form of I/O, but it does seem to be winning. And the trick for optical I/O is at least the way we see it is make the fiber look as close to dumb wire as possible. So whatever the signal is that's coming in, our goal in life is to take the electrons and make them photons and send them out optically. So I think that's going to be key to enabling the broad ecosystem as well. So yeah, I think standards.
Let me ask you a question. When I'm thinking about it. How is that different from the way silicon photonics was being done at rack scale stuff, 10 years ago, 5 years ago? How is this different? How is this approach different?
Well, so yeah, a good question. So our approach is, we develop an electro-optical chip that gets integrated inside of a package, right? So most of the optics so far we've talked about it are pluggable transceivers that you plug into the back of the server. There's been some talk about, there's an industry alliance called COBO where they're trying to take the optics and putting it on board. And you can think of what we're doing as just bridging that final mile, taking those optics all the way into the chip, just like Mark was talking about earlier. Why go through that electrical trace, going out through a package pin onto the board to the end of the chassis or to some component to then just translate it to optics? Why not just speak optics directly out? And it's going to solve some of the problems that Mike spoke about as well, like power, pin limitations, latency, all those things.
All right, Mike, he brought you up, so tell us your thoughts.
To me, yeah, I agree. CXL looks like it's getting a lot of traction within the industry. And for good reason. It enables a lot of new innovation on both accelerators and shared disaggregated memory. I personally think CXL is going to usher in a new wave of innovation in the industry. And I'm very optimistic about that. In terms of CXL over optics, you can actually do that fairly easily if you own both ends of the link.
Right.
And the trick is to enable the industry to connect different components from different vendors over a CXL optical link. And that's going to take some standards work. There is no CXL over optics standard right now. And whether that's done through the CXL or some MSA or some combination of the two, I don't know the answer. But that's going to be the next thing the industry really needs to work on to enable both optics and CXL to fully reach what they're capable of.
Mark, are you banking on CXL over optics to fulfill your needs?
No, I'm completely confused at the moment, to be honest, because I've sat in multiple presentations from, say, HPE about Gen Z, for example.
Oh, I was going to get there, but go ahead, bring it up.
No, I think it's, from somebody in my position, it's just unclear, right? And at some level, I don't mind as long as there is some sort of standardization. That's the important thing.
Well, what I've been told, how I should think about it, is stop making them compete with each other. It's CXL inside the chassis and Gen Z outside the chassis. And I'm like, well, no, you don't just throw something out there. If it's running over photonics and it can do low latency and long distance, then people are going to use it in unnatural ways. That's people. They're going to look at what one costs, and then they're going to do things that make sense to them. And we might get memory servers, what do you call it? It's not a server. What is it? It's a memory block. I don't know what it is. Based on both protocols. Like you, I would like it to make sense. So, Craig, makes sense. He brought up Gen Z. I didn't do it.
I'm sorry.
Sense. Yeah. Nobody told me I had to make sense. So a couple of things playing off some of the comments that were made. So first of all, if you look at how standards are developed, I'm going to date myself again here, but Ethernet versus ATM, right? Huge debate in the late 90s. And did Ethernet win because it's better, or did Ethernet win because it's used? So what's used today is PCI Express off of server chips. So we make server chips. We're limited in terms of the amount of beachfront we have to put interfaces on. So we can't put everything. That's clear. If I'm coming off the chip and connecting up to optics, I prefer it's something that I have an interface for today. So CXL, okay. So, standardized solution, this is perfect. De facto standardized. If we want to go to Gen Z, we can put a bridge on the board from CXL to Gen Z, and now you have a bridgeable solution so that it works at the system level. But you can put that on the board, right? So I think having one standard, as Mike said, that supports memory, supports accelerators, can support chip-to-chip interconnect. So that's all good. I think the coherence is built in, and it'll come generation to generation. It'll get better and better. So I guess the question is, why not CXL? I'd rather have 1 than 10.
Yeah, we got too many right now, and it caused problems. I mean, IBM refused to put NVLink on Power 10. Okay, how are you going to win that deal?
Yeah,
you lost the deal because of it. It's a real thing. So, are we going to have to still reckon with Gen Z though? Does anybody want to take that? I mean, is it still going to be there? Is it going to be part of this? Will there be confusion and competition for that? Because that's got co-packaged optics too. Anybody? Ian?
I was going to reserve my opinion on that until after ISC, to be quite honest.
I will accept that answer if everyone agrees they don't want to do all that right now. That's fine.
Better yet, after this week, right? Yeah.
Yeah, I guess we did. Time will tell, I guess. But they can coexist is the point, and I've seen them coexisting. And they don't want to battle. The two consortium don't want to battle each other. They want to improve system architecture. And so did everybody at all the vendors that were backing that alphabet soup. Everyone got together and they decided, okay, all the members of all those other protocols are on the CXL consortium too. So we all want something to be better. We all know it's going to be hybrid and disaggregated and all this stuff. So I think it's safe to say that we're going to figure it out in a less painful way than, say, I don't know, every other I/O standard from the last 3 decades. All right, so another question here. Can silicon photonics get rid of all of the electrical I/O signaling? This is another thing I keep thinking about. Like, can PCI keep up, or will PCI be this legacy thing that we have in a server where there's a tiny little chip if you need it, maybe on a MES card or something? I don't know. And that all the I/O coming out of a CPU should be in some fashion co-packaged optics. Hugo, go ahead.
Well, it certainly could. The question is, would you do that, right? I think, our view is anything that needs to be high bandwidth, high performance, low latency, low power, you're going to be able to do that better in optical, right? But there's things like telemetry and system management and other kind of low speed, low power buses that you might look at and say, well, electrical is just fine. Right?
Well, we could do that. You could do that like you do with the legacy I/O controllers in an Intel chipset. They don't put it on the CPU; they put it on the Lewisburg chipset, and they, yeah, sure. If you need that PCI Express card, yeah, you can do it.
Sure, sure. But I mean, if you think of it, you're always going to have your power and ground pins on your CPU or your memory, right? So you are going to have electrical paths into the chip, and I would say it's analogous to when you take your Ferrari out versus when you take your minivan out, maybe. And sometimes minivans just perfectly fine.
I don't have a Ferrari.
Well, I don't have a Ferrari.
Well, I have a Yukon and a Challenger. That's sort of like, the American farmer version of that. Craig, what do you think? Can we get rid of PCI and just have, the protocols that used to run on top of it?
So if everybody went to the same protocol, like Mike was saying, it'd be fantastic if you're just running something really optimized for optics right out of the chip, and that was connecting up to everything else through optical switches. I mean, that would be lovely. But if I look at, you still have, fiber channel, you still have 1 gig Ethernet out there today. Things have a long tail. So what exists today is going to exist in 10 years or 15 years, especially the bleeding edge stuff, right? That's going to have a long tail. So I think you're going to find that people use the interconnect that's, best suited for the application, whether that's price, reliability, all the different elements they need for that interface. And they're going to make a choice each time. Now, future proofing is also part of that choice. Mm-hmm. But I think optics has a place to play. But replacement, I mean, let's talk about timeframes. It's not in the next 10 years, right? It's just too much out there.
Mark, what do you think?
Yeah, I think I completely agree with Craig there, actually. In fact, Tim, you were teasing me about the 200 gig Ethernet earlier because I did waste my money in it, or rather invested in it.
I didn't know that. Oh, I'm so sorry.
Yeah, so we just moved to that. But interestingly, the data center management network, the system management network we put in, we decided, well, we won't go for 1 gig any longer, we'll go for 10 gig. And actually, we had terrible problems with that, buying cheap 10 gig switches and doing so. Actually, most of it is now back in 1 gig land. And that wasn't what we intended at all. But that's just because of the world that we live in terms of controlling your systems in your data center, just happens to be a 1 gig Ethernet world today. And I agree with Craig, that is not going to change anytime soon.
No, I didn't suspect that would change, but I want to corral it and make it as small a part of the I/O as possible and open up as much for all this new stuff. Mike, I've forgotten, did I ask you?
No, you didn't. I'll just say that our product planning and business folks will not approve of abandoning PCIe electricals completely off our.
I meant over the longest of terms.
Yeah, I mean, I suppose our product planning folks would still be saying, I'm assuming there's going to be a PCIe Gen 7 followed by PCIe Gen 8 by the end of the day.
I want to get rid of it at 8.
Yeah. I think the interesting question is not for mass market CPUs or GPUs, but what about pooled memory or specific accelerators? There, I could see the possibility of products coming out with optical interfaces only. that makes a lot more sense.
I agree. Yeah, the memory is the natural place to start, and it's the biggest problem. You've got stranded memory in these machines like crazy. And there's sometimes when you really want a large block of memory for a small number of server cores, but you don't want to pay for that every day of your life.
Right.
That's insane. I think are we ready for Q&A? I think we're ready to start Q&A. Unless if you guys want to have some closing comments or something before we start Q&A, feel free to say something. If I haven't asked a question that you think needs to be answered, this is a good time.
So I had one point I was going to raise there, which Mike just said. So we're moving to a world, as we move to exascale systems, largely of a CPU surrounded by 4, maybe 8, but generally 4 GPUs. But the big change is that we're going to a single address space in most of these systems, some with high bandwidth memory, some without. Do you think that plays into this optical move? Do you think that actually helps us with that? Or do you just think some of the vendors are going to say, well, I'm not going to go to optical, I've solved the memory problem?
So, I look at this as, we have a server that has 4 physical GPUs, but that's just because it's more efficient to put 4 GPUs in a single box than it is to put 1 per box, and it helps with scalability. No one is basically running a single MPI rank across 4 GPUs, except that they're running only a single node job, and that's not an exascale job. So, to some extent, the mental model of the applications is already that, every GPU essentially is its own MPI rank. And so, I think it's already at the point where a server is not an aggregated thing unless it's only that server, because the network off the server is so slow that, there's still that full step function that was mentioned earlier, even within the box. And so once you're dealing with the step function, you're dealing with the slowest step function.
Right. I'm back to smashing the server again. I'm going to say it out loud. The data center is a collection of DPUs, and the CPU is a serial accelerator for it, just like a GPU is a parallel accelerator for it. Get used to this idea. No operating systems, runtimes only. All right, I'm done.
So you're giving the CPU too much credit. The CPU is the orchestration engine. It's the conductor, and that's it.
Oh no,
it's not even a serial processor.
It's not even that. All right. Well, for some workloads, come on, give it some work.
Oh.
All right. Anybody? Anything else you want to pipe up?
I'll just say that, as Mark mentioned, CPU and 4 GPUs as a common configuration is a statement about the packaging limits and the electrical wiring limits. And if you can transition to optics, it's not clear that 4 GPUs is the right answer anymore.
That's right. I think it's a rack of GPUs, a half rack, or a quarter of rack of CPUs. It's going to keep shrinking. The more I talk, the smaller it gets. I love that idea. I just don't know. And we didn't talk about this, but one of the things that we have to realize is that you'll be able to independently upgrade and configure things. It's not just the composability, it's the buyability or the not buyability. I can have a bank of memory that is just fine, and I can use it for 10 years. We can't do that now. We know the memory will last, and we can throw the CPUs out as we see fit. It's the ability to buy and replace things completely independently, I think, is a powerful concept. And we haven't been able to ever do that. So I don't think we quite do the math on how important that might be. It also might mean that there's a lot of really, really ancient crap in our data centers for a very long time. And that may not be a good thing. I don't know. All right, I think it's time for our Q&A. And I think the one thing we didn't talk about here, and someone's brought up, is what's the time frame for this? What's the time frame when co-packaged optics is going to be normal? What's the time frame when CXL will be normal? It's not really here yet. Hugo, you can ship ahead of CXL being practical. So yeah, you win.
So. Yeah, I think you're going to start seeing some of the first POCs, proofs of concepts, coming out this year. The first system that I can point to that will have co-packaged optics in it will be making an appearance in 2022. Actually, the first couple of systems will be, and then you'll see even more and more adoption after that. So it's really around the corner. versus being seen as a far out technology. So obviously I can't talk about the customer systems, but we should be seeing them very soon.
All right. Well, I'm eager when you're ready to talk about it. Obviously, Ian, when do you think this is going to happen? What's the way this rolls out? I think I'm going to guess because it's fun. It's going to take baby steps. We're going to get some composability and aggregation, decomposability, aggregation. Yeah, you're right. It doesn't work. I'm going to stick with the original language. Disaggregation and composability to start, probably with accelerators, maybe with memory, maybe with some storage. How's this going to play out? And what
Yeah,
time?
I mean, we're starting to play with AI accelerators over the network because that workload is very amenable to it. It's high compute, low input. You put in a little bit of data, you get out a little bit of data. You do this really complicated, calculation, and we're seeing that at least from a practical standpoint is possible. Now we have to fully demonstrate it on systems, but the breaking up of nodes is going to start to happen over time as well. So there's two types of disaggregation. There's this kind of composing different types of compute resources, which for certain workloads can happen even without optics. And then there's what optics is going to enable, which is these pools of memory or other things, which probably are more in the 5 to 10 year range as the steps start to happen. Even though the photonics will start.
Let me interrupt for a second. Can memory be pulled over electrical now and still be useful, or do we really need the optics and the low latency and high bandwidth to do it properly? What's your guess?
For most applications, you're going to need higher bandwidth than you can get. For a few, you could probably pool with what you have today, but they're the few that could potentially take advantage of and don't need the bandwidth; they need the capacity.
Right.
But you have to not be bandwidth or latency sensitive, and that's mostly not HPC. That's going to be in other domains.
Right. I mean, I saw a Gen Z memory server. I'm using that term probably incorrectly, but I liked it very much. I thought it was very, very interesting that it's a chunk of memory on a light pipe that a number of servers could all connect to and take a partition of as they saw fit. They were doing that a year and a half ago. I mean, it's a prototype, but it kind of points in the direction of the kind of thing you could do. Craig, what do you think?
Well, a lot of thoughts, actually. If we look at open architectures today at the silicon level, you see people putting different, so not even at the silicon level, let's talk at the server level. You see all kinds of different accelerators, right? So you see how many AI accelerator companies do we have today? I mean, that's a really fertile ground. Yeah, sure. They're not all going to survive, but so looking at then what you can connect a CPU to drive, whether it's in package with OCP ODSA, so you're looking at a chiplet marketplace, right? So you can put different chiplets in a package, or whether you're looking at different sockets on a board, you're looking at all kinds of disaggregation already in the way you can compose these elements together. So that's going to happen no matter what, whether it's over electrical or optical. Optical just gives you the distance to play with that. I don't know. I see that the market's already moving in this direction.
All right. Mark, you've got roadmaps for systems. You want to think about how this stuff might come to your machines. What do you think? When do you think it's going to start being practical?
I always get nervous at this point because you always forget when you've done an NDA briefing and when you haven't,
Just pretend you have something. We're all friends here. It's all good.
Yes, indeed. I think I actually thought it was going to happen sooner than I now do. So there was a lot of talk 2 years ago, 3 years ago from a certain individual who you will all know, but we're not going to talk about here. And I thought really that things were going to happen in the next 18 or so months. I don't think that's going to happen any longer. I mean, Hugo can't say anything, but I'm sure he's got some things up his sleeve, of course, but I wouldn't say from the briefings I'm getting at the moment for our exascale system, which will be operational in 24, nobody's trying to sell me for that. So I think you're probably looking at the second set of US exascale systems for this sort of stuff really to be rolled out, would be my best guess.
Well, Mike, you're probably involved in some of this stuff, so you can't say anything, but I'm going to poke you.
Yeah, what can I say? I think Hugo is basically right. We're going to see proof of concept systems coming out in the next year or two or so. And a lot of that is actually going to be around proving that you have a co-packaging system that you can actually scale to higher volumes when you're ready, and checking out the reliability of those systems and so on. And then just very short few years later, you can start seeing in higher volume, high-end components as part of an actual product roadmap. And I'm kind of expecting the next generation of exascale procurements to be including a lot of optical interconnect in the proposed systems. I think that would happen.
So in networking, we always want performance to go up, but we want the cost to come down too, and the cost per bit has to come down. What's going to happen there with cost? You know, is this going to be great bandwidth, but you're going to pay more for your network, and you know, or is it going to solve the cost problem too? Will it come down enough? You know, the 400 gig was delayed with Ethernet for this very reason. It's like everyone said we can't get the transceiver costs down. It wasn't the switch ASIC that was the problem, it was the transceivers. And I think it's been 4 years that they've been trying to change the laws of physics, and I think they've got some of the laws bent enough that it's actually going to be affordable, and that cost per bit comes down. So who wants to tackle that? Raise your hand.
So I think there's two things here, actually. It's not just about the cost of the transceivers, but it is partly about the cost of the transceivers.
Sure.
But at the next generation of exascale systems, we've got to reduce the power requirements. So most systems are going to sit about 20 to 25 megawatts for just over an exaflop today. There's absolutely no way I can go beyond that in my data center. So, you know, and most sites are pretty much having those sort of discussions. And one way to achieve lower power consumption is to get rid of all the transceivers and to do the optical bit on the processors. I think that's a key way, the key next step for these really large systems.
Or near the processors, as you
exactly. Yeah. Nearer.
Intel puts them on, IR puts them near it, and you guys have your laser outside. Intel has its lasers inside. I think that's if I'm characterizing it correctly, Hugo. Correct me if I'm wrong.
No, that's right. We disaggregate the lasers for a number of different reasons, but you know, really it comes down to it's not about the laser at all. It's about those traces and the energy that it takes, and the energy you're taking away from the socket to drive the I/O off chip, right? So by some measures, maybe 25 to 35% of the power in a data center is just going to moving data around. And being able to take those signals out of the ASIC directly, out of the CPU directly, optically cuts down the power by 90%. So you know, that's going to have a huge impact on the power footprint of your data center. You know, the other cost component,
that's like 7 megawatts right there in his budget, in his power budget. I mean,
it's going to be significant. The other cost components you should think of is, first off, you know, we're talking about silicon scale here, and we know how silicon scales over time. So from a cost perspective, the core materials, I think you'll see a dramatic scaling over time. And then overall system topologies, right? What's it mean when you don't need 24, 36, 48 ports at the top of your rack, right? Maybe you only need 1 or 2 ports up there, and your rack is your new socket. It's your new pool of compute,
or a pod
so
that stretches 3 watts.
It could be multiple racks, right? So I mean, it's important for us to look at the overall system and solution cost, not just say, you know, how much is one component versus the other.
Well, I guess I'll ask it that way then. Will the cost per bit for the collection of I/O that's done within a 3-rack, you know, region in a data center, will that come down if we do that? And if it does, and if it comes down a lot, and you get all this performance, and you can have composable infrastructure, then this seems like a no-brainer. And in my mind, if you have those degrees of freedom, you'll pay a little more for it, maybe. And I'll say this, you correct me if I'm wrong, gentlemen. I'll pay more money, but I won't pay more power. There's no way I'm paying more power, but I'll pay a little more money for that. Does that make sense?
I would agree with that. Being the person that ends up paying the money.
Ian, does that make sense?
I think we'd pay more power if we saved money, because our power rates are so cheap, unlike our European colleagues, and our capability to go up to 40-ish megawatts is more than most people, right? We have a data center that's going to have 85 megawatts of.
So you get to go first. You can have the part that has all the energy draw. And you guys can
but it's got to be
later.
But it's got to be cheaper or enable something in terms of performance. It has to enable a system that's more performant, even if the cost per bit doesn't go down. And I think Hugo's right. It's at the system scale. If it gets you something at the system scale, even if it itself does not make things cheaper, that's okay.
But if you didn't have to buy HBM memory accelerated CPUs and GPUs, and you could just buy CPUs and GPUs and had memory blocks of DRAM, that'd do it, I think.
Yeah. Then we could pay more for the network that connects it all together, right? It's at the aggregate system what you deliver to people running jobs. That's the end of the day. You can mess with the balance of cost, you can mess with the balance of power, but the dollars that you spend need to be more efficient overall.
Craig, any thoughts?
Yeah, I think the other side of this is maybe a little more political too, which is green data centers, right? So that's you can think what you want about politics, but they play a part in any acquisition. So if the world's driving green and you can be greener, it'll help. It'll help getting funding.
It definitely does, and more so. And not only that, these kinds of systems being greener it's an easy thing to point to. They can wave that flag high. Mike, what do you think? Can it get cheaper?
Yeah, it can. All the big component manufacturers, Intel, AMD, NVIDIA, they're trying to figure out how to get to the next doubling of compute performance within a socket, knowing that they'll get very little benefit from CMOS improvements. And part of the answer has to be pull power out of that socket that's not directly involved in compute. So that's what's driving and what's going to be driving a lot of this in the industry, to these big component suppliers. And I definitely see the benefits of eventually going to co-packaged optics there.
All right. And I think we have time for one more question here. Hugo, I think this is aimed at you. Can co-packaged optics be used for CXL over optical? I think we talked about that one. I got the wrong one. What is the chip-to-chip silicon status of chip-to-chip silicon photonics? My apologies, I read the wrong one.
What's the question again, Tim? I'm sorry.
What is the status of chip-to-chip silicon photonics? So I guess they're pulling you into that thing that Mike was just referencing.
Yeah. Well, I mean, the status is it's here now.
Okay. Well, that was easy.
Just last week at the OFC conference, we demonstrated the world's first terabit per second link, full duplex, 2 chips docked to each other over fiber. So with the external laser source and everything. So the technology's here, and it's a matter of all the integration work that it takes to get the chiplets into the socket. Of course, there's the next step of taking those new sockets and integrating them into systems. There's the software that has to come together. So, a lot of different pieces in the industry have to come together to make it a consumable technology. But the base technology of the 2 chiplets being able to talk to each other, it's here now.
Well, good. Glad to hear it. I think we have to leave it there, gentlemen. Thank you so very much.
Thanks, Tim.
Thank you.
Thank you.
All right. Cheers.
Cheers, guys.